One more 5, and Dad's got a Yahtzee here. Can I see something out the window there? Yahtzee! I got it! Ha Perfect! Oh, hi there. Hi. Didn't see you come in there. Just playing some Yahtzee here. As you can see, I managed to roll my 5 and get my Yahtzee. We're going to talk about probability today. So here's a really simple probability question. I'm sure you know the answer. What's the probability of rolling a 5 on a single die? Well, there are 6 possible outcomes on a die, and only one of them is the desired outcome, the 5, so the probability is 1 out of 6. I'm sure you don't find a question like that very difficult. But that's where probability begins. So what we're going to look at now is we're going to introduce something called set theory, because some of the probability concepts that we're going to learn involve sets and counting. So we're going to begin with set theory, and we're going to show how we can solve some simple probability questions along with learning some set theory notation. Okay, come on, let's take a look. Before we can do any more work in statistics, we really do need to start talking about probability. Now, probability is useful in itself in that there are questions in probability that are interesting to know. I mean, we can look at stuff like what's the probability of winning the lottery and those kind of things. And also, we've kind of hit a point where we've been talking about normal distributions and means and medians and modes and sampling. We really can't go any further without introducing probability into that. So we need to start with experimental probability. So the idea with experimental probability is that you could look at the probability of rolling a 5, and one way to calculate the probability of rolling a 5 was to perform an experiment. Roll the die over and over and over and see how many 5s you get. You would expect that about 1/6 of the time you would get a 5, but that's not a guarantee. It would depend on the experiment. You might be unlucky and get less than 1/6 of your rolls being 5, or you might be lucky and get more, assuming you want to roll 5s. The next step of probability is theoretical probability, and that's kind of what we think of as like the real probability. So theoretical probability is given by this equation here. It's the number of desirable outcomes divided by the total possible outcomes. So the probability of rolling a 5 is the number of outcomes that result in 5 divided by the total possible outcomes. So our number of outcomes that result in the 5 is 1. There's only one way to roll a 5, and there are 6 possible outcomes. Now keep in mind, this assumes that all outcomes are equally probable. Okay, that comes very important later. We're going to talk about set theory now too. There's a few reasons we talk about set theory. It is helpful in figuring out probability. Also, a lot of literature uses set theory. Your textbook uses set theory, and I think you'll find a lot of online resources use set theory as well. So I want you to be comfortable with some of that notation. I won't ever force you to use it in this course. A set, to start with, is simply a collection of things of the same kind. For example, we could talk about the set of the days of the week. I could call that set W. It's common to label sets with capital letters, and in this case I can use squiggly brackets to simply list the elements in this set. If you've done domain and range in grade 11, you've probably seen set theory when working with domain and range as well. The set of teachers at Saugeen District Secondary School, that could be a set. The set of numerals on the 6 faces of a die, I'm calling that S. Okay. Now in the previous example I used S because this set represented all the possible outcomes in rolling a die, and it's common to use S for that set. It's kind of like the universal set in that world of rolling a die, all the possible outcomes you could get. The set of all possible license plate numbers in Ontario, that is a set as well. The set of all possible 5-card poker hands. So here's one element of that set. That's a very good poker hand. You got dealt 3 aces and 2 kings, and that could be one element of the set, and there are many others as well. Each item in a set is called an element of the set. An element either belongs to a set or not. There's no repeats. You don't list it twice in the set. Example, 1 is an element of the set of all rolls in a single die, but 7 is not, of course. Talking back to the days of the week set, W, notice this notation right here, N of W equals 7. That refers to the size of the set. So the number of elements in set W is equal to 7 for the 7 days of the week. We could also talk about the number of elements in S. okay, which is equal to 6 rolls. And believe it or not, if you were to go through and look at all the possibilities of being dealt 5 cards from a well-shuffled deck, you would find that there are almost 2.6 million possibilities that you could have. And that is even keeping in mind the fact that it doesn't matter what order you got dealt these cards in. There's still 2.6 million possible outcomes when you receive 5 cards. And believe it or not, in this course, we're going to be able to figure out answers to questions like that when we get into what's called counting methods. They're counting the number of poker hands that are possible. There's also an empty set. It has a size of 0, and its notation is that 0 with a little slash in it. In fact, we could write that the empty set is just equal to those squiggly brackets with no elements in it. Okay, set theory and probability. We can now adjust our formula for probability of an event A happening using this formula right here. We could say the probability of event A is equal to the number of elements in set A divided by the number of elements in set S. If set S is all possible outcomes, and set A is the set of all outcomes corresponding to event A happening. So back to our rolling of 5, the reason that we get 1 out of 6 is the set that corresponds to all possible outcomes has a size of 6, and the set that corresponds to what we're looking for, event A in this case, is just the set we're happy with a 5. And so the size of that is just equal to 1. Let's talk about the complement now. When you think complement, think, I'm going to write this down even, think opposite. Or think not. The complement of set A is usually written as A apostrophe. We tend to pronounce that as A prime. And consists of all the outcomes that are not in the set A, but are in the set of all possible outcomes. So A prime is the outcomes in S that are not in A. This in S just kind of means like, in the universal set, but not in the set we're looking for. So you can kind of ignore that and just think about not A. I'll give you an example. So this is actually our 5-sided rolling a 5 example again. So if our desired outcome A is to roll a 5, and the set of all possible outcomes is 1, 2, 3, 4, 5, 6, then A prime would be everything but a 5. So everything in the universal set except for our 5. Now this comes into probability because the probability of A prime will always be given by 1 subtract the probability of A. And in our example, we're saying, imagine I now ask you to come up with the probability of not rolling a 5. One way to calculate the probability of not rolling a 5 would be to say it is 1 subtract the probability of rolling a 5. So 1 subtract 1/6, which is 5/6. If I ask you what the probability of not rolling a 5 is, you might think of it that way. You might think about taking the probability of 1, which is like 100%, subtract a 6th and get 5/6 for your answer. Or you might also think about the 5 other numbers that are not 5. It doesn't matter. We refer to this as finding the probability using the complement. And although, I'll just get rid of this so it's not in the way here. This is important for difficult examples later on. Sometimes calculating a probability of an event happening, it's easier to calculate the probability of the event not happening. And we call that using the complement. Example, when you draw a random card from a deck, what's the probability it is not a king? One way to answer this might be to take 1 and subtract the probability that it is a king. So use the opposite. Well, the probability of it being a king, there are 4 kings in a deck of cards. There are 52 cards in a deck. Okay, 4 different suits, 13 cards each. Well, that's just 52 over 52 minus 48 out of 52. Which actually reduces to 12/13. Maybe that's how you come up with that answer. Maybe you just look and you say, hey, there's 48 cards that are not kings divided by 52. I don't really care how you do it. I just want you to understand the idea of that we can use the complement. The next thing we should talk about in set theory is the idea of OR, which is called the union of 2 sets. The union of 2 sets is the collection of elements that are found in at least one of the sets. So imagine we have over here set A and set B, okay? The union of A and B is, we use this notation here. You could think U for union. It can be thought of as A or B. And notice all the elements in A and all the elements in B are shaded. That's called a Venn diagram. I'm sure you've seen that before. Consider our die example. If A is 1, 2, and B is 5, then if we union A and B, we have 1, 2, and 5. There's also the intersection of two sets, which we refer to as and here it is in the Venn diagram. So if we have A and B as these two circles, and we want to talk about the set of elements that are in A and B, you can see that it's shaded in here. And they have to be found in both of the sets. That should say intersection, I'm sorry. The intersection of A and B is given by this notation right here. So the upside down U. And can be thought of as A and B. I like to think about this little symbol here as kind of looking like an A. I don't know if that helps or not. Consider our die example. If A is 1, 2, and B is 5, then the union of A and B would be the null set since A and B have nothing in common. Here's a different example. If C is 3, 5, 7, and D is 1, 2, 5, 7, then A intersected with B is 5, 7 because they have a 5 in common and a 7 in common. Okay. Now notice in this example here, we got our intersection to be the null set. If two sets have nothing in common, then their intersection is the null set. And we actually use the word disjoint. That are called disjoint sets. And that's what the Venn diagram for two disjoint sets would look like. Notice they don't intersect at all. Okay, disjoint sets are important when it comes to probability. In fact, we call A and B mutually exclusive events if their intersection is equal to the null set. So I know we're talking about sets, but in our course, sets correspond to events that are happening as well, like rolling a die. Mutually exclusive events are events that cannot happen at the same time. Okay. If we want to know the probability of A union with B, or A or B happening, we can just calculate the probability of A and add it to the probability of B, provided A and B are mutually exclusive. So anytime you see like this symbol, you can think of this as the probability of A or B, okay, because it's the union of the two sets. Example, what is the probability of rolling a 5 or a 6 on a single die? Well, the probability of A or B, you can think of event A as rolling a 5 and event B is rolling a 6. Well, the probability would be the probability of rolling a 5, which is 1 out of 6, and the probability of rolling a 6, which is also 1 out of 6. And so our probability is 2 out of 6, or 1/3, 33%. That's pretty simple. Okay, most of you, I'm sure, wouldn't actually need to add a 6 to a 6 to get this. You just look at this and say, well, if you want to roll a 5 or a 6, that means you're happy with the 5 or the 6, so there's two outcomes that you're happy with. But I just want to talk more generally about mutually exclusive events. If you have event A and you have event B and you want to know the probability of one or the other happening, you can add their probabilities together provided they are mutually exclusive. They can't happen at the same time. In this case, you cannot roll a 5 and a 6 at the same time. I don't care how much you cheat. You roll a 5 or a 6 or something else, but it can't happen at the same time. Okay. So there's just reviewing what we said on the last page there. Okay. Suppose I roll a die. What is the probability that I roll a 5 or I roll an odd number? So imagine you tried to add these probabilities together again. The probability I roll a 5 is 1 out of 6. The probability I roll an odd number is 3 out of 6, since there are 3 odd numbers. So I might say that my probability here is 4 out of 6. Well, that is actually incorrect, and I hope you realize and can kind of see why. There are two reasons that we can argue that this is incorrect. One reason is we can look at all the outcomes. The outcomes are 1, 2, 3, 4, 5, 6. How many of those outcomes am I happy with? Well, I'm happy with 3 of them. Rolling an odd number or rolling a 5, and I've circled the 3. So the real probability here is actually 3 out of 6. Now, why did I get it wrong by adding these probabilities together? Because these events are not mutually exclusive. I can roll an odd number and a 5 at the same time, since 5 is an odd number. Had I changed the question to roll a 5 or an even number, then yes, you could add those together because they are mutually exclusive. You can't roll a 5 and an even number at the same time. So what do we do when events are not mutually exclusive? How do we calculate their probability? Here's another example. Suppose I flip a coin and roll a die. What's the probability I roll a 5 or flip heads? Again, we might look at it this way. You could say, okay, well, you flip a coin. You roll the die first. Doesn't really matter what you do first. The probability of rolling a 5 is 1 out of 6. The probability of flipping a head is 1 out of 2. So if we look at that, that's 3 over 6. Sorry, that's 1 over 6 plus 3 over 6. It's 4 over 6. Or we could say 2/3. That is also incorrect, and I can show you why that doesn't work. The reason it doesn't work is because we can actually list all of the outcomes. Imagine rolling the dice. You could get a 1, 2, 3, 4, 5, or a 6. And suppose you happen to get a heads when you do that. So 1H, 2H, 3H, 4H, 5H, 6H's. There are 6 of the possible outcomes of rolling a dice and flipping a coin. There are also 6 more though, because you could have a 1 in a tail, a 2 in a tail, a 3 in a tail, a 4 in a tail, a 5 in a tail, and a 6 in a tail. Now, how many of those outcomes am I happy with? Well, let's just count. Flip a coin. You want to roll a 5 or flip heads. Well, I'm happy with all 6 of these. But I'm also happy with this one right here. So there's actually a 7 out of 12. That is my real probability of this happening, which is actually lower than 2/3. It's not quite the same. Okay, well, obviously we need a strategy here. Consider the union of two non-mutually exclusive events. So union is again talking about or. I want to know the probability of A or B. The number of elements found in A union B, set A or B, can be found by adding elements in both sets and then subtracting the number that have been counted twice. So if you imagine wanting to know how many elements are in A or B, well, if I added the elements of A, we'll say that this is set A, and I added the elements of B, do you see that I would double count the elements in the middle? So what I can do to take that into account is that I could say the number of elements in A or B is the number of elements in A plus the number of elements in B, subtract the number of elements in the intersection, which is this like middle part right here. Sorry, I shouldn't be using red. So what happens when I add A and I add B together, I add the intersection twice. I double count those elements, and so I can subtract them. So when we talk probability, the probability of event A or B happening is the probability of A plus the probability of B, subtract the probability of A and B happening at the same time. So, well, how do we do this for rolling a 5 or an odd number? Well, the probability of rolling a 5 is 1 out of 6. The probability of rolling an odd number is 1 out of 2. The probability of rolling a 5 and an odd number is 1 out of 6. There's only one way to do that, rolling a 5. And sure enough, we get the real answer to this question, which is a half. The probability of rolling a 5 or an odd number is actually the same as the probability of just rolling an odd number. How about back to this one? Suppose I flip a coin and roll a die. What is the probability I roll a 5 or flip heads? Well, the probability that I roll a 5 is 1 out of 6. And the probability that I flip a head is 1 out of 2. Subtract the probability that both things happen at the same time. Now, if you remember, I actually wrote out all the possibilities. There were 12 of them. Okay, so the probability that I rolled a 5 and flipped heads, that only happens once here. So that's actually 1 out of 12. So this will give you the real probability. 1 out of 6 plus a half minus a 12, which is the same as 2 out of 12 plus 6 over 12 minus 1 over 12, which gives you 7 over 12. So I'm showing you that the formula here works for calculating the probability of two non-mutually exclusive events. Okay. However, like, keep in mind, getting this 7/12, it's much easier just to write all the possibilities out and then realize that 7 of them are the desired outcome out of the 12. So I'm just showing you that the formula works, even though it's not very useful in this case. Find the probability that when you draw a card from a 52 card deck that the card is either a jack or a spade. Okay, so we're talking about either, so we're talking about or. Okay, so we want to know the probability that you draw a jack or spade. So we could take the probability of a jack, add that to the probability of drawing a spade. Okay, that's the spade symbol right there. And then we need to subtract the probability that both happen. Now notice I'm using or and instead of the union symbol and the intersection symbol. You can do whatever you like here. So the probability of getting a jack, there are 4 jacks in the deck. And the probability of getting a spade, you could look at that either 1/4 or 13 out of 52, since there's 13 spades. It doesn't matter which way you do it. Subtract the probability, it's the jack and spade. Well, there's only 1 card. There it is right there. So that's 1 out of 52. So I get 17, subtract 1 is 16 out of 52, which actually reduces, if we divide by 4, to 4 out of 13. And there you go. Now, you could get this 16 out of 52 many different ways, obviously. I mean, one way to do it is you could just look, say there's 52 cards in the deck, 13 of them are spades, plus there's 3 more jacks that I'm also happy with. I get 16 cards. Absolutely. Like I said, we're just doing simple examples to understand why formulas like this work. Notice that this is the formula for calculating the union of 2 probabilities, or the or aspect of 2 probabilities. If these sets were disjoint, then notice that this probability would be 0, and it wouldn't matter. You're subtracting 0 anyways. In a class of 25 students, 11 are wearing blue jeans and 8 are wearing a hat. 10 students are wearing neither. If a student is picked at random, what is the probability the student is wearing jeans? Well, this isn't too difficult. There are 11 wearing jeans out of 25 students, so 11 out of 25. That's our probability as a fraction. We can also write it as a decimal as well. That's 0.44. We can also write that as a percent, 44%. If a student is picked at random, what is the probability the student is wearing blue jeans or wearing a hat? That seems like, well, if we look at it, there are 10 students who are wearing neither. So that means that 15 students are wearing one or the other. Notice I'm kind of using the complement there. That's 15 out of 25, which of course reduces to 3/5 as well. What is the probability they are wearing just a hat? Okay, when I say they're wearing just a hat, I mean they're not wearing blue jeans. They're hopefully wearing more than just a hat. Okay, so we need to think a little bit about this. This requires just a bit more thinking. One way we could do it that's kind of interesting, if we say that H is the students wearing a hat, and J is the students wearing jeans, we can come up with this little formula right here. The probability that a student is wearing a hat or jeans is equal to the probability they're wearing a hat plus the probability they're wearing jeans, subtract the probability that they're wearing both. Okay. Well, I know the probability that they're wearing blue jeans or a hat. That's 15 out of 25. The probability they're wearing a hat, well, 8 students are wearing a hat. The probability they're wearing a jeans is 15 out of 25 from above. Subtract the probability they're wearing a hat and jeans. That's actually what I want to figure out. And I get this little formula that I can now solve. So if I just rearrange it a bit, I can see that the probability of a hat and genes would be equal to, so bring that over there and it becomes positive 8 over 25 plus 15 over 25. Take away 15 over 25. Sorry, I made a mistake there. That should be 11. There are 11 students wearing jeans. So that should be 11 there. That makes more sense. So 11, 8 plus 11 is 19 minus 5. I get the final answer. There are 4 out of 25 that they're wearing a hat and jeans. Now I've included a little Venn diagram here. You could calculate this probability using a Venn diagram. We know there's 25 students in the class. We know that 10 are not wearing any blue jeans or a hat. So there's 10 people outside of, if we consider this to be H, the hat group and the jean group, there are 10 that are in neither. Okay? So then if there are 10, that means that there's 15 that belong to both. Now if we add 8 and 10, we get 18. Sorry, not 8 and 10. If we add 8 and 11, people wearing jeans and the people wearing a hat, we get 19. Okay, so it can't be 19. That kind of tells us there must be 4 students that are getting counted twice. Just like that. And then wearing jeans is 11, so there must be 7 people here. And 8, there must be another 4 people here. Okay, so all I'm doing is kind of going through the process of elimination. So 25 minus 10 is 15. There's 15 people that are in one of these groups. Okay, and so 15 people, but there's 8 in this group and 10 in this group. That's 18. Sorry, there's 11 and 8, which is 19 in both groups here. Okay, so that's got to be 4 too many, counted too many. So I know 4 must be like double counted that are in the intersection there. I hope that made sense. I feel like I got that out kind of awkwardly. There's your Venn diagram there. So if you look in OneNote, you should be able to find these homework questions I've assigned. I've made one just involving some simple set theory, and the rest is from your textbook. Now, please look in OneNote if you don't have your textbook. I have uploaded some of the pages for you to use for homework questions and included the answers as well. Feel free to read through your textbook as well. Section 4.2 and 4.3 use some of the same examples I did, but they explain most of that material. So hopefully between my video and the textbook, you'll be able to understand that and look for some more stuff on probability coming up soon. Okay, thanks for now. Good luck.